Welcome back to TalkTensors, listeners. Today we're diving deep into some really fascinating research that's taking on a huge challenge. It's all about figuring out cause and effect in the sprawling, complex world of cities.
Yeah, it's pretty ambitious.
Oh, definitely.
But that's what makes this paper so exciting. It's called, get this, Causal Discovery and Inference towards Urban Elements and Associated Factors.
Catchy, right?
Catchy, yeah.
But don't let the title scare you off. The core idea here is actually something we grapple with all the time, even outside of urban planning or machine learning.
It's that age-old question of correlation versus causation.
Right, like just because we see two things happening together doesn't mean one is actually causing the other. There could be all sorts of hidden connections we're missing.
Exactly. And in a city where you've got millions of people, businesses, buildings, all interacting in this incredibly intricate web, those hidden connections can really throw you off if you're trying to understand how things work.
Especially if you're trying to make decisions based on that understanding.
Oh, absolutely.
Like, imagine you're a city planner and you notice that neighborhoods with more parks also tend to have lower crime rates. Tempting to think, okay, let's build more parks. Problem solved, right?
Right.
But what if it's not the parks themselves that are causing the lower crime? What if there's some other factor, like higher average income, that's driving both the presence of parks and lower crime rates?
You'd be investing in parks, maybe expecting a certain outcome, and end up completely missing the mark.
Exactly. And that's where this paper comes in. It's basically saying we need to get smarter about how we figure out what's actually causing what in cities. They're proposing this whole new framework built around machine learning to really dig into those causal relationships. And they're not just talking theory here, they're actually putting it to the test using real-world data from New York City.
Yeah, and it's fascinating stuff.
It really is. So for anyone who wants to follow along, we'll have a link to the full paper down in the show notes. But don't worry, we're going to break it all down in plain English.
As always.
As always. So let's start with the problem statement. What are these researchers trying to solve? Well, they're saying that relying solely on correlation analysis in urban studies can lead to some pretty misleading conclusions. And they're not wrong. There are countless examples of studies that have found correlations between various aspects of city life. But then when you dig deeper, those correlations turn out to be spurious or misleading.
Yeah, like you might see a study that says, hey, there's a strong correlation between the number of coffee shops in a neighborhood and its walkability score.
Yeah.
And on the surface, it might seem like, oh, more coffee shops, more people walking makes sense. But what's really going on could be something else entirely. Maybe it's the areas with a certain type of zoning or a certain demographic makeup are more likely to attract both coffee shops and people who prefer to walk. So the correlation is there, but it's not telling the whole story.
It's like seeing the shadow of something, but not the actual thing itself. And what these researchers are trying to do is build a way to see the actual thing, to identify the real underlying causal connections that are shaping our cities. And to do that, they've developed what they call an urban causal computing framework.
It's a pretty elegant solution, actually. They break the whole process down into three main stages. First, you got to gather all the relevant data about the city. They call this urban factors acquisition. Then comes the really cool part, where the machine learning comes in. That's the urban causal computation stage, where they actually try to discover and quantify those causal relationships. And finally, they test how well those discovered relationships hold up by seeing if they can use them to make accurate predictions about urban mobility patterns. That's the urban causal prediction stage.
Okay, so let's walk through each of those stages one by one. What kind of data are we talking about here? Where are they getting it from? What's in it?
So for this particular study, they focused on New York City, and they used data from 2019 and 2020. They divided the city up into these small geographic units called census tracts, which gave them a pretty granular view of things.
How many census tracts are we talking?
Over 2,000, I think.
Okay, so quite a bit of data.
Oh yeah, lots of data points.
Yeah.
And within each of those tracts, they gathered information on three main categories of urban elements: citizens, locations, and mobility. So for citizens, they looked at things like the total population, the breakdown of males and females, the percentage of minors and elders, the median age of residents, and the poverty level. Pretty standard demographic stuff, but essential for understanding the makeup of each neighborhood.
Right. And then for locations.
Locations, yeah. They categorize the different types of businesses and establishments within each tract, like how many transport facilities are there, entertainment venues, restaurants and cafes, educational institutions, and shopping areas. It's basically a snapshot of what kind of amenities and services are available in each part of the city.
And then finally, mobility. What did they track for that?
For mobility, they looked at how people are actually moving around within and between these tracks. They measured things like the percentage of people who commute by public transport, the average travel time to work, and a more general measure of population movement or flow. It's all about understanding how connected different parts of the city are and how people are using the transportation infrastructure.
And where did they get all this data? I mean, it sounds like a lot to pull together.
Oh, yeah, they used a bunch of different sources. For the demographic data, they went straight to the U.S. Census Bureau. That's kind of the gold standard for that kind of information. And then for the location data, they tapped into OpenStreetMap, which is this amazing open source mapping project where people all over the world contribute to building a really detailed map of the planet.
I love OpenStreetMap. So much cool data there.
It's amazing. And then for the mobility data, they use something called the Origin Destination Employment Statistics, also from the Census Bureau. That data set tracks where people work and where they live, which gives you a pretty good picture of commuting patterns.
So they've got all this data nicely categorized and organized. Now what? This is where the machine learning kicks in, right?
Yeah, this is where things get really interesting. The goal of the urban causal computation stage is twofold. First, they have to actually discover the potential causal relationships between all these different urban factors. And then they have to estimate the strength and direction of those relationships, taking into account any confounding factors that might be muddying the waters.
Okay, so how do they do that? How do they teach a machine to understand cause and effect in a city?
Well, for the first part, the causal discovery, they turn to reinforcement learning, or RL for short. It's a technique that's been getting a lot of attention in the AI world lately. You might have heard of it in the context of game-playing AI, like AlphaGo or those Dota bots that can beat professional players.
I've definitely seen those videos. Pretty mind-blowing stuff.
Yeah, it's crazy. But the basic idea behind RL is that you have an agent that's interacting with an environment. The agent takes actions, and those actions lead to certain outcomes. Based on those outcomes, the agent gets rewards or penalties, and it learns to adjust its behavior over time to maximize its rewards.
So in this case, the agent is like the machine learning algorithm and the environment is all this urban data, right?
Exactly. And the actions that the agent takes are basically proposing different causal graphs. A causal graph is like a map that shows how different variables might influence each other. So the algorithm might say, okay, I think that the number of parks in a neighborhood directly influences the crime rate. And that would be represented as a link between those two variables in the causal graph.
And then it gets rewarded or penalized based on how well that proposed graph fits the observed data.
Exactly. The tricky part is that the space of possible causal graphs is absolutely massive. There's so many potential connections between all these urban factors that it quickly becomes what's called an NP-hard problem. Basically, it means that finding the absolute best causal graph, the one that perfectly explains all the data, is computationally infeasible. It would take longer than the lifetime of the universe to calculate.
So they need a clever way to navigate that huge space of possibilities and find a good solution without getting lost in the weeds.
Yeah, and that's where RL shines. Instead of trying to exhaustively search through every possible graph, RL algorithms use a more strategic approach. They learn from their mistakes, they explore different parts of the search space, and they gradually converge on a solution that's both plausible and statistically sound.
And for this particular study, they actually used a pretty sophisticated neural network architecture within their RL model.
Oh yeah, they went all out. They combined a transformer-based self-attention encoder with an LSTM-based decoder. It's a mouthful, I know. But basically, these are types of neural networks that are really good at processing sequential data and understanding long-range dependencies. In this case, that means they're good at figuring out how different urban factors might be influencing each other over time and across different parts of the city.
So after all that number crunching, they come up with a potential causal graph, a map of how these different urban elements might be connected. But that's just the first step, right?
Yeah.
They still need to figure out the strength and direction of those connections and account for any confounding factors that might be skewing things.
Right. And for that, they use a technique called propensity score matching. It's a statistical method that's been around for a while, but it's really powerful for teasing out causal relationships, even in messy real-world data.
Okay, break that down for me. How does propensity score matching work?
So let's say you want to understand the causal effect of, I don't know, let's say the presence of bike lanes on the number of people who bike to work in a neighborhood.
Okay, yeah, that's a good example.
The problem is you can't just compare neighborhoods with bike lanes to neighborhoods without bike lanes and assume any difference in biking rates is solely due to the bike lanes. There's going to be all sorts of other factors at play, right?
Like maybe neighborhoods with bike lanes also tend to have younger, more active residents who are already more inclined to bike, regardless of infrastructure.
Exactly. Those are the confounding factors we talked about earlier. And propensity score matching helps you control for those factors by creating these statistically matched groups that are similar in terms of all those other potentially influential variables, but differ in the one thing you're interested in this case, the presence of bike lanes.
So you're essentially creating these artificial control groups, like in a scientific experiment.
Exactly. And once you have those matched groups, you can compare the outcomes, in this case, the biking rates, and have more confidence that any differences you see are actually due to the bike lanes and not those other confounding factors.
I see. And in this paper, they're applying propensity score matching to all sorts of urban factors, not just bike lanes.
Okay, yeah, they're using it to analyze everything from the impact of median age on mobility flows to the influence of poverty rates on the availability of certain types of businesses.
And they're even going a step further by using something called ordinal regression.
Right. That's because a lot of these urban factors aren't just binary, like bike lanes or no bike lanes. They exist on a spectrum. You could have a neighborhood with a few bike lanes or a lot of bike lanes or some in between. And ordinal regression lets you analyze the causal effects across those different levels.
So it's like a more nuanced way of measuring cause and effect.
Exactly. And once they've estimated those causal effects, they calculate something called the average treatment effect, or 8E. It's basically a way of quantifying the overall impact of a particular urban factor on the outcome they're interested in. And they use statistical tests to make sure those findings are actually meaningful, that they're not just random noise in the data.
So they've discovered the potential causal relationships. They've estimated the strength and direction of those relationships. They've accounted for confounding factors, and they've made sure their findings are statistically sound. What's left?
Well, the final stage is to see if all this hard work actually pays off. Can they use these discovered causal relationships to make accurate predictions about how people move around the city? That's the urban causal prediction stage.
So it's like the proof is in the pudding, right?
Yeah.
If they've truly identified meaningful causal links, then those links should be useful for making predictions about the real world.
Exactly. And that's exactly what they found. They focused on predicting 3 key mobility indicators: overall population mobility, the rate of public transportation usage, and the average commute time. And they found that when they used only the urban factors that their causal analysis had identified as having a significant impact, their prediction models performed better.
So it's not just about understanding causality for the sake of understanding. It's about using that understanding to build better models that can actually help us make better decisions about how we design and manage our cities.
Right. And they also found that using these causally informed models helped to prevent overfitting, which is a common problem in machine learning. Overfitting is when a model learns the training data too well and ends up performing poorly on new, unseen data.
It's like the model is memorizing the answers instead of actually understanding the concepts.
Exactly. And using a causally informed approach helps to avoid that by focusing on the factors that truly matter, the ones that have a genuine causal influence on the outcome you're trying to predict.
Okay, so they've built this framework, they've applied it to real-world data, they've validated their findings. What did they actually discover? What are the key takeaways here?
Well, one of the most interesting findings is that they identified this clear 3-tier hierarchical structure in the urban environment. At the top of the hierarchy are the characteristics of the citizens themselves, their demographics, and socioeconomic status. Those factors have a causal influence on both the types of locations that are present in a neighborhood and independently on the mobility patterns of the residents.
So it's like the people shape the places, and both the people and the places shape how people move around.
Exactly. And then in the middle tier of the hierarchy, you have the locations themselves. The distribution of things like transport hubs, commercial areas, and residential zones also has a causal influence on mobility.
So it's like a chain reaction, with each level influencing the one below it.
Right. And this hierarchical view is really valuable because it gives us a framework for understanding how different aspects of a city interact and how interventions at one level might cascade down to other levels.
Makes sense. And what about specific causal relationships? Did they find anything surprising or counterintuitive?
Oh, definitely. They found a bunch of cases where the causal relationships were quite different and sometimes even opposite to what you might expect based on simple correlations.
Give me an example.
Okay, so they found that a higher median age in a neighborhood actually causes a decrease in overall mobility flow. Now, if you just looked at the correlation, you might see a positive relationship there. Older people, maybe they're retired, they have more time to get out and about, right?
Yeah, that's what I would have guessed.
But the causal analysis revealed that it's actually the opposite. When you control for all those other factors, like income levels and family structure, older residents tend to be less mobile overall.
Interesting. And what about those confounding factors? Did they find any specific examples of how those can lead to misleading correlations?
Oh, yeah. They highlighted a few cases where correlation analysis would have led to completely different conclusions than their causal analysis. Like, they found a positive correlation between median age and the number of shopping locations in a neighborhood. You might think, okay, older people, more disposable income, more shopping. But it turns out that correlation is confounded by the rate of minors living in the area.
Ah, so maybe it's not the older residents who are driving the shopping, but the families with kids?
Exactly. And they found similar examples with the relationship between median age and overall mobility, which is also confounded by the presence of minors, and the relationship between the proportion of elders and the number of education locations, which is confounded by the poverty level.
So it's like those confounding factors are like hidden variables that are messing with the equation.
Yeah, they're like those optical illusions where your brain sees one thing, but the reality is something else entirely. And without a way to account for those confounding factors, you're basically flying blind when it comes to making decisions based on data.
Okay, so to summarize, this paper is making a really strong case for why we need to move beyond simple correlation analysis and start thinking more causally about urban systems. They've developed a framework that leverages machine learning to uncover those hidden causal relationships. And they've demonstrated that using a causally informed approach can lead to better predictions and more effective decision-making.
Absolutely. It's a big step forward in the field of urban science, and it has the potential to really change the way we plan and manage our cities.
It's exciting to see how machine learning is being applied to these big real-world problems.
It really is.
So now it's time for our favorite part of the show, the novel notions segment. This is where we take the core ideas from the paper and start brainstorming some potential extensions, some what-ifs that might spark further research or lead to unexpected applications.
Always fun to speculate.
So one thing that struck me is that this paper focused on a relatively static snapshot of New York City using data from just 2 years. What if we could apply a similar framework to analyze how these causal relationships evolve over time?
Oh, that's a good one. Like, imagine you could track how the causal links between different urban factors change in response to a major event, like a natural disaster or a pandemic.
Or even just in response to policy changes, like the introduction of a new public transportation line or a zoning change.
Yeah, that would be fascinating. You could start to build these dynamic models of urban change, where you can actually see how different interventions ripple through the system over time.
It would be like having a crystal ball for urban planning.
Right. You could start to anticipate unintended consequences or identify those leverage points where a small change could have a big impact down the line.
And another thought I had is about the level of granularity. This paper looked at data at the census tract level, which is already pretty detailed, but what if we could go even deeper? What if we could apply these causal discovery techniques to individual level data?
Oh, wow, that would be amazing. Like, imagine you could build a model that understands the causal factors that influence an individual's transportation choices, their access to healthcare, their exposure to pollution.
It would be like taking precision medicine and applying it to the urban environment.
Exactly. You could start to design these hyperlocal interventions tailored to the specific needs and constraints of individual residents.
Of course, there are huge ethical considerations there, especially around data privacy and the potential for bias. But if we can address those challenges, the potential benefits are enormous.
No doubt. It would be a whole new era of urban planning, one that's truly centered on the needs of the people who live in our cities.
It's something to think about for sure. As always, we'll be keeping an eye on this area of research and reporting back any interesting developments. In the meantime, if you're curious to learn more about the specifics of this paper, we encourage you to check out the link in the show notes. And if you have any thoughts or novel notions of your own, we'd love to hear them. Hit us up on Twitter or drop us an email. Thanks for listening to TalkTensors.
Until next time.